So my screen is visible to everyone.
Yes, sir. Is it
Yes, sir.
visible?
Okay. Okay. So good evening, everyone. Welcome to the tutorial session of materials characterization of week 4. So as we do, we will go through this the concepts and concepts that have been taught by the professor throughout the week. And then we'll go through some problems which is related to also which will be related to the concept. Okay. And so in the last class, actually what we have studied is about light optical microscope. That means microscope means anything that we want to see, we cannot see with our unaided eye, but we want to resolve those small features in a material. And so first what we did, we used light as our source. Incident we first we impinge the material with incident beam, and the light means generally when we talk about light optical microscope, we talk about in the wavelength range of 400 to 700 nanometer. Then we use that light, white light, or different microscope also, different types of light. So we used different modes of operation. Through different modes of operation we used, and we used the light, and we saw some structural features of the material. But yeah, there a formula was there, if we remember, that is I am writing, that means the optimization is 0.61 lambda divided by there we have written n sin alpha. So this formula, if I am talking about this optimum, so that is the minimum resolvable distance between 2 points. That means this is the resolution, that's what we call it as. So this told us about the resolution that our microscope can have, or how much distance we can see between 2 points. So here, if we notice one thing, by so that means the less d will be there of our for our microscope. Let's say I'm designing one microscope, the less d will be there, our microscope will be better. Why? Because less d means my microscope is able to, let's say my light optical microscope is able to earlier is able to give me the resolution in the order of d1. Let's say the distance is d1 here. My light optical microscope earlier, with the wavelength of 400 to 700 nanometer, any wavelength in between, was able to give me the resolution in the order of d1. Let's say now I decrease my decrease my wavelength of the incident light, then what will happen? Let's say now this distance is d2. From this formula, if I am putting this formula, as my wavelength will be decreasing, then my microscope's capability to distinctly distinguish between these 2 points will also decrease. That means my resolution of my microscope, it will effectively, what I will say, that my resolution is increasing. So that is the reason that from light optics, right, from light optics we are going to electron optics. And what is the difference between the light optics and electron optics? One of the difference is that here the incident beam is made up of electron. Okay, so that is why we will be seeing the currently we will be going to electron optics, and subsequently we will see how electron optics is used for seeing the grain structure, different composition, different diffraction geometry in a material. So, and for your to get an information like how the wavelength of light varies with the wavelength of the electron, if I am talking in that term, so the wavelength of light, if you talk about light wavelength, it is in the order of if I am talking in terms of angstrom, it is in the order of 4000 to 7000 angstrom, 400 to 700 nanometer, right? But if I am talking about electron wavelength, if I'm talking about electron wavelength, it is in the order of, so this is 4000 to, so this is in the order of 0.04 or sometime 0.06 sorry, so in the order of this angstrom. That means this is for if you want to compare, so this is this is in the order of 400, let's say 400 nanometer, and this is in the order of 4 picometer, right? So the wavelength variation between light and the wavelength variation of the wavelength of the electron, that is in the order of thousands. So from here I can see that if I change my beam from light to electron, I will be able to get I will be able to get much more information that I was initially getting from light optics, right? So this is the reason that this is one of the primary reason that from light optics we are switching to electron optics, right? But there are this is one of the benefits that we will be getting, that we will be getting one better resolution. But then there are also some disadvantages coming with electrons. What are the disadvantages? One of the major disadvantages is electrons are much strongly scattered by air than light, right? If we are to generate an electron microscopy, we cannot generate just like we are doing, we are keeping one lens here in light microscopy. This is our let's say illuminator. This is our illuminator, which we are just this is let's say this is our object, we are just illuminating, and somehow we are getting some image so this is our object and this is our image we are getting, and n also we are considering that this is air, refractive index are also air. But here electrons we cannot do that. Why? Because electrons are strongly scattered by air. Air means there are different types of gas molecules are present, like oxygen, like nitrogen. All those molecules will be scattering the electrons that are coming. Why? Because these molecules are heavily they are having protons and neutrons in their nucleus, so they will be either attracting, or in some cases the electron repulsion will also happen, which between the electrons of these gas molecules and the electrons of our incident beam. So that is the reason they are much more strongly scattered by air. So this is one of the reason why for which we need vacuum. So that is why in electron microscopy, be it scanning electron microscopy or transmission electron microscopy, the the process of image collection is different in scanning electron microscopy and transmission electron microscopy, but the fundamental mechanism behind this scanning and transmission electron microscopy are same, because in both cases what we are doing, we are allowing electron beam to fall on our sample and then give us crystallographic information or microstructural features, right? So this is one of the major disadvantages for which we also for which we need vacuum to view our image. And in light optics, what we are doing, we are considering the refractive index of the medium. Here the refractive index depends on the electric or magnetic field. Why we are using electric or magnetic field? Because since electron is a negatively charged particle whose charge is 1.6 into 10 to the power minus 19 coulomb. So and we know that any if this electron travels in electric field or magnetic field, then it will experience some amount of force on it, so it will be easily deflected. And how we can control that thing? We can control that thing by providing by increasing or decreasing the magnetic field strength, right? So this refractive index was working in light optics microscopy. This refractive index of the lens we are calculating, this is a physical lens. However, in electron optics there are no physical lens present here. So refractive index in an electric or magnetic field depends on the field strength. Based on your field strength, let's say you are applying very high field strength, then your electrons will be refracted strongly. If you are applying very low field strength, then your electron might be reflected weakly, right? And based on this concept, Snell's law has been given, where the electron beam, instead of light, electron beam undergoes refraction, and the refraction formula is given by sin r by sin I is equal to square root of v1 by v2. So here v1 by v2 are not velocity, they are potential, right? So here okay, I have written all these things. So here if you can just look at this image, if you can look at this side of the image. So here you can see this is v1 means lower potential here, right? And v2 means higher potential. So from lower potential to higher potential, when the electron is going, it is getting refracted. That means its path is getting changed. Based on this concept, we used to use the electrostatic lens, that from higher potential to lower potential the electron will be refracted, right? So this is the concept behind the electrostatic lens. So here this is, let's say, from this is our electrons are going, and from here, like some case we are so electrons, once electron goes out of its source then it will go in all sorts of directions, not only in 2D but also in 3D. And how to constrain those electrons to diverge in a three-dimensional direction, we will see in the microscopy, that how one cap called Wenelt cap, it has been given, right? So it will go in all directions, since this is electron negatively charged, right? So if we will put all these things here, this is also another negative charge. If we put it, then what will happen? It will start repulsion will happen, and in that repulsion, the electron which were initially going like this, they will start, initially they were diverging, now they will all start converging here, right? So this is the mechanism behind the electrostatic lens. Electrons, once they come out of their electron gun or the electron source, they will start to diverge. Now electron, if we are to give any kind of negative potential across its path, then they will again start to converge. And if we want to compare this is the light optic, and this is the electron optics, right? Same thing, what the thing that glass lens was doing, that it was focusing all these incident beam onto a particular, this is the object, this is the image, it was focusing everything onto the image plane. If I am talking about, if I am trying to put any detector here, it was focusing on the image plane. Same thing here also, the electron. So this is the electron beam, and if I am putting any negative thing here, then it will also, so this was earlier diverging, now what it does, it is converging all the thing. And finally all the electrons which let's say my electron beam is coming to a point, and I will be able to use the electron as I was using the light rays here. So this is the reason for the electron optics to be that generated. And so why we we know that electrons also, electron is a charged particle, but similarly proton is also a charged particle, same charge but opposite positively charged particle. So the thing about electrons is, don't look at this table right now. I'll explain what this non-real is, this accelerating voltage and relativistic wavelength and non-relativistic wavelength in a minute. So when we electron being a negatively charged particles, let's consider its charge currently as E, right? So when a negatively charged particle like electron accelerates through a accelerating potential, difference, okay, then when this electron is accelerated through a potential difference of V, then its energy will be given by EV, right? And this energy is the electron will be having this much of potential energy, right? And this energy will suddenly give electron to move at a very faster rate, right? So since this electron now has gained this amount of energy, so we know that this potential energy, if the electron starts to move, because it is now accelerating. Now accelerating means it will again, the static electron will gain some energy which is in the form of kinetic energy. Now total potential energy which electron has is ev, right? And when the kinetic energy, electron gains some kinetic energy, then the potential energy will be equal to kinetic energy. In that case, let's say I am saying the electron is mass of the electron is m, and so this is small v square, right? So this is my kinetic energy and this is my potential energy. These two should be always equal, and the velocity that I will be getting from here is equal to 2e, this is capital V by m, me, yes, so the square root. So this will be the my velocity of the electron through which electron will pass when I am when there is a potential difference of capital V. And now the thing is, we know that the relativity theory of Einstein, and that theory, when we it is the ideal case. So this thing is the ideal case, right? And but when the relativistic effect acts on the electron when it is going at a very higher speed, right? So at that time what will happen, the mass of the electron will start to decrease due to this relativistic effect, and the mass will increase. How it will increase? I am just writing one equation, right? 1 minus v by c okay. So the mass of the electron will start to increase as it gains some velocity, and suddenly what will happen, its velocity, when you this velocity is now dependent on this accelerating potential, right? This potential difference, as you increase the potential difference, this velocity will also increase, and as the velocity will increase, the mass of the electron will, due to the relativistic theory, the mass of the wavelength will also start to mass of the electron will also start to increase. In that case, so the mass of the electron will increase. That gives that will, once the mass will increase, then what will happen, this thing ev, the potential energy that the electron has gathered, that will also start increasing, right? And subsequently, so it will be like one action will be giving to another action. So that to make the long story short, once you increase the accelerating voltage here, as you go down, once you increase the accelerating voltage, you can see both the relativistic wavelength as well as the non-relativistic wavelength, both wavelength, so they will also start decreasing. Here you can see the accelerating voltage is in the order of 100 kV. So this table actually I have taken from one TEM, transmission electron microscopy, but the same concept is also applicable to scanning electron microscopy. So here you can see the accelerating voltage when I am giving to one electron is 100 kV. The wavelength here, if you want to check, this is in 0.003, that means you can see 3 picometer, the wavelength, right? And if I am increasing my accelerating voltage to 1000, here in this case you can see this is 0.8 picometer. As I said previously, the less our wavelength will be, the more and the finer structure we will be able to see in our through our microscope, right? And as you see, the accelerating voltage, when you increase, the velocity will also increase, and the mass of the electron will also, in this you can see it is also increasing. But these two are not important from a microscopist point of view, but if you want to see this wavelength is certainly decreasing. And this is the reason, if our wavelength is decreasing, we always want our wavelength of our radiation or incident beam to decrease, right? So this is the reason we go from if you see in a SEM microscope, from 5 to 30 kV, we restrict ourselves from 5 to 30 kV, because we do not want to this is for a TEM, this table, but for SEM, if we want to see some microstructural surface topography, then we restrict ourselves to 5 to 30 kilovolt. You can say that beyond 1000 will also we can go, but that will also create some other kind of problem which we will see in the subsequent slide, right? And this is the so that was the concept of electrostatic lens. And then if we come to electromagnetic lens, that means both electric field as well as the magnetic field are present, and they are acting on the electron beam here, right? So these are all the electron beams. Since electrons are, always remember, since electrons are negatively charged carriers, so it is easier for us. Instead of you can ask also same thing we can do through glass lens, but the problem is the penetration power of electron is very very poor. If electron is traveling and in the path of the electron you put a glass lens, the penetration, the electron, even with its higher energy, it cannot penetrate this glass. So that is the reason we have to remove this glass lens and put some lens which is not a physical lens, but which acts as a which is a virtual lens but acts as a physical lens, right? So that is the reason we are going to electromagnetic lens, and this electromagnetic lens will deflect our electron beam based on their energy, based on their energy, and based on their wavelength, right? And so here is, so these are all the pole pieces like all the so this is a pole piece around which the wires are, conducting wires are there. So this is, let's say, a pole piece around which the conducting wires are there, and once we start giving a potential to them, then what will happen? Around these wires, the magnetic field will be generated. We are giving electric potential to these wires, and around them the magnetic field will be generated. Since the magnetic field will be generated, we know that if any charge carrier will go in the electromagnetic field or the magnetic field, then they will experience a force. That force will be given by, right, this is the E is the E I am just saying because we are currently considering the charge of the electron. So this is the charge of the electron, V is the velocity, and V is the magnetic field. Okay, so this is the reason it will experience some amount of force, and what force size, what is the force direction, that is more important to us than what is the magnitude of the force. So that is why we have chosen electromagnetic lens as our to act as our virtual lens for the electron beam, right? And yes, here if you then in light optics, what you are seeing, light optics means we are not considering that always whatever we are putting in the path of our light, we are changing it like this. Even if some kind of so this is the object, this is our image, even if some kind of aberration is there, so we always, while ray tracing, will always we did straight path, right? For light optics we did. And even if we had to consider it at a certain point of time that light can act as wave instead of particle, then also we more or less choose the path like this, right? But in the case of electron, what will happen? And in light optics, this was a horizontal. We were horizontal tracing we were doing, though the in practical situation the light can come vertical, but here we will be talking in terms of vertical tracing we will be doing. So what will happen here? Now if you see, so this is so B is my magnetic field, right? And this V here that you are looking at here, this is my velocity. So don't look at here. First let's see the velocity. So this is my pole pieces are there which is generating. So this is the path of my electron currently right? And let's say at a certain point of P, right, at a certain point P I am taking, at this point my one of the electron beam comes and interacts with this point. So at point P only, my electron beam first interacts with this magnetic field, right? So what will happen at P, and beyond P, beyond this one, my electron beam has not yet interacted with the with the magnetic field. So what will happen now? Let's say my electric field is B, right? And my, so that means if I want to break down my electric field into two vector, one will be B radial, another one will be B longitudinal. Okay, so now the force that my charged particle will experience will be V into B, right? It is a cross product of velocity into velocity with the magnetic field. So here what will happen? V into B, that means VV sin theta. Effectively this will be VV sin theta. If you see, the V is parallel to BL, right? That means in this case sin theta will be 0. That means the force that my electron beam will experience due to this longitudinal component of the magnetic field will be, let's say I am saying longitudinal component of the magnetic field will be 0. However, the force, this velocity will be perpendicular to the radial direction of the magnetic field. That, so in this case, so the force that my incident electron beam will experience due to this magnetic field will not be equal to 0. So how you calculate that? Okay, it will not be equal to 0, but what will be the, I am not interested in the magnitude, but I am more interested in the direction. What will be the direction of this force that I am getting? So if you look at that, okay, for a moment I'm just look at my video. So here what will happen? If I, so the force will be given by, since it's a cross product, the force will be given by Fleming's right hand rule. So if I'm considering, so Fleming's right hand rule means I'm taking three fingers here, right? So if I'm considering that my velocity is this direction, right? My velocity is the velocity is given by my thumb, and the radial component of the magnetic field is given by my forefinger. That means if I am talking velocity, if I am saying that the velocity is given by this, and my forefinger is giving the my radial component of the magnetic field, then the middle finger, this will give me the direction of the force, right? I hope you can see. So this, so I am tilting a little bit. So this is my direction of the incident electron beam. This is my which is perpendicular to it, the forefinger is giving the direction of the radial component of the magnetic field, and my middle finger is giving the direction of the force. That means my incident electron beam is getting a force towards the center, towards when I'm rotating my finger throughout on 180 degree, always the direction of the force that my incident electron beam is getting, it will always be away from it, right? So this is the region. What will happen? So due to that, what will happen? The electron will always experience a spiral kind of motion, right? And this is the region, and the moment it gets deviated from perfectly vertical motion, it gets deviated a little bit, then what will happen at that point? Let's say it's just at this point, just it got deviated a little bit, and at that point what will happen? This B longitudinal, that means the longitudinal component of the magnetic field which was not working on this incident electron beam, it will also start working at that point. Now what will happen? Both of this radial component as well as the longitudinal component, when they both start working on this incident electron beam, the electron beam will not be coming straight, rather the electron beam will always start in this motion. It will be going, first it will be going spiral, then it will be going in a helical motion, Okay, so this is the reason, and we are not sure how much spirality happens for one incident electron beam. So that's why in an electromagnetic lens, when we are imaging something, we will always get an image which is a little bit rotated. It has nothing to do with the distortion in the image. It has nothing to do with the image distortion. It does not degrade our image distortion, but we are getting a rotated image, right? So that is how the force on the charged carrier acts, and then the electron beam starts to rotate and go in a helical path, right? And then so based on these concepts, so how to use the means based on the concept of using the electron as our incident beam, and electron beam as our incident beam, and electromagnetic lens as our electromagnetic lens system to deflect the electron, we have used scanning electron microscope. As the name suggests, scanning, that means there is a specimen surface and our electron beam goes and falls and then scans across this surface, right? And since it scans across this surface, it's a raster scan, right? Since it scans across this surface, then that is why the name suggests scanning electron microscope. Electron means the incident beam is made up of electron, right? So electrons are used to create images of the surface, and the resolution that we are getting, it's in the order of 1 nanometer to 5 nanometer. And since the atomic distance that we are talking of, that is in the order of angstrom, so that is why even if we want to see, though the scanning electron microscope, it's almost like 250 times greater the it gives you the magnification and also resolution, a much higher resolution it gives as compared to the light optics microscope, you still cannot see the atoms, but we are able to see much more finer details than we are able to see in light microscope. And there are different kinds of electrons that we use to image our sample. One of the most used name is secondary electron, and another one is backscattered electron. These secondary electrons are called as AC, and backscattered electron are called as BAC. So when we want to see the topographical image, or there are the different fractography, then so this is generally used for topographical image, and this BAC is used to jet contrast or phase identification, or phase contrast you can say, right? And this SEM gives us the 3D view of exteriors of the object. That means we can see we can see exteriors of the object, means the surface I am talking about. Since the electron cannot penetrate the surface of the in SEM, sample size does not matter. That is one of the benefits of using SEM, because we can have a thin sample, we can have a thick sample, but still we will be able to see if their surfaces are good enough, right? So these are some of the features of scanning electron microscope, and this is a scanning electron
Excuse
microscope.
me.
Yes.
Secondary electron for factography. Why? Can you explain again, please?
Yeah, secondary electron for fractography, because in the so once you get the fracture surface, so what will happen, some will be valleys, some will be hills. It's like this kind of some things will be there, right? So in those cases, what we will do, the so depth of focus of the scanning electron microscope is very high if you use the AC mode, right? So this is the reason we generally implement the scanning secondary electron, because what will happen, let's say your incident beam is coming and lots of secondary electrons are generating so there is an effect called edge effect, right? So the edge effect means, let's say I am having a flat surface and I am having an edge kind of surface here. So in this edge surface, when in the edges, the number of secondary electrons will be emitted at a very large quantity. Since the number of electrons that will be emitted in a very large quantity, my detector can easily detect the secondary electron, right, after interaction with the specimen. Since and edge, so this will be very large edge compared to when my incident beam comes, and let's say these are the secondary electrons generated, in this cases, then due to this edge effect, so much larger amount of secondary electrons will be generated, and that thing will help me seeing the the topography of the fracture surface. Since my fracture surface will be having many valley hills, it is a hilly kind of structure, so that is why the secondary electrons are used for this fractography study. Yes, so this is an image of the scanning electron microscope. So this is it's not a very big instrument, but still big enough so that first so this is on the table on which it is kept. Beyond it, here this, so for us to use a scanning electron microscope, we need, I told you, we need vacuum, right? And the vacuum in the order of 10 to the power 5 10 to the power minus 4 Pascal, that in that order we need. Generally, if we see like our atmospheric pressure is 10 to the power 5 Pascal, so we need vacuum in the order of 10 to the power minus 5, that means 10 to the power 9 times 1 billionth of our atmospheric pressure we need for electrons, so that we will be effectively seeing our specimen. And this is what it's called as electron column. I'm just writing electron column, and this is the area where this is our sample stage. So we'll be creating vacuum here through vacuum pump, and then we'll be this thing will be pulling out, and we will be putting our sample. And these are the different kind of detector. The BSC detector, not sure which one is which detector, but these are the different types of detector attached to the sample. And then from this side we will be having control system, and we will be seeing our image, right? And this is an instrument. The mechanism of a scanning electron microscope is like this. We generate electron using some source or electron gun. Then, since I told that once you generate the electron gun, electrons will be diverging in a conical structure in all 3 dimensions, right? So we need some sort of lens, and that lens which brings all the electrons to a particular focused point, and that lens is condenser lens. Okay, and so condenser lens will bring all the diverged electron into a point, and that will be, and it will focus all the electrons, and then after focusing it will also go again. After the electron beam will pass through the objective lens, right? And objective lens, according to our requirement, the objective lens, we will capture all the beams, and then what the objective lens will do, it will start focusing onto the specimen. So the job of condenser lens is not to focus the electron beam onto the specimen. The job of condenser lens is to focus the electron beam so that it will, so here what we are saying, that the diameter of our electron beam should be very fine. So this is the point where we want the diameter of our electron beam should be fine, right? And then all the electrons will be again coming out, because you cannot control the motion of the electron if you leave them freely. So again, objective lens will try to focus them onto the specimen here, and in between there will be scan coils, and also different set of lens system are also nowadays attached, so that less number of aberration we have to face. And then after the electron beam interacts with our specimen, our detectors will be there. It will scan all through this specimen, and then this is the detector. From detector, amplifier, and then cathode ray tube will be there, and then finally you will get your image. So this is our image. So this is the mechanism, like electron is generated, focused by condenser lens, and passed through by objective lens. Then again it is focused to specimen. Before focusing, we use also, this is term called aperture, based on our whether we want to see we want to use all of our electron beam onto the specimen, or portion of the electron beam onto the specimen. This aperture defines that. Why we want to limit some of the incident electron beam, so that we will be able to get a very fine probe here, very fine probe. And sometimes also some samples are, since these electron beams are very highly energetic, we don't want our samples to be contaminated. So that is also another reason. And also some charging effect happens if our sample is not conducting. So we in that case, what we do, we limit the intensity of the electron beam which is falling onto our sample, right? So this is the mechanism of this is the mechanism of scanning electron microscopy. Okay. And yes, so now we will go through one by one component. So one of the component is the electron source. So electron source is one of the major thing that has to be integrated with scanning electron microscope. And there are two types of electron sources are there. One is so electron source, those things are called as electron gun, right? And so two types of electron guns are there. One is thermionic gun, another one is field emission gun. In thermionic gun also there are two different type of materials are there. One is tungsten wire, another one is lab 6, or this is called as lanthanum hexaboride. And in field emission gun there are three types of guns are there. One is cold field emission gun, another one is Schottky field emission gun, and the third one is thermal emission gun. So there are different types of these are, so this is a tungsten thermionic gun, this is a lab 6, and this is a cold fade. So what is the mechanism behind this electron emission from the electron gun? So the mechanism is generally, if we heat any material, let's say I am taking any material, this is material M. If we want to heat any material beyond a certain temperature, the electrons and light particles both will start coming. So what is that temperature? That temperature is 2700 Kelvin. If we heat any material beyond 2700 Kelvin, and both light and as well as the electrons will start coming from that material. So this is the reason thermionic means we are heating a particular material. We are heating a particular material, and by heating we are giving electrons energy, so that they will have enough energy, so that they will jump from they have the energy to overcome their work function, right? So that is the reason we are heating the material, so that electrons will have enough energy. And but the problem is heating the material beyond 2700 Kelvin is a difficult task, because not many material are having that much high melting point. As well as here you see this is a hairpin kind of structure. Why hairpin kind of structure? Because if you take a very thin material, then there is high probability that even after applying a temperature of 2700 Kelvin or 2800 Kelvin, the electrons will easily start coming out. If you take a very thick material, in that case electrons will come out, but not in the large quantity as you would have expected earlier. And also the time to which electrons come out from a thin material will be very large in case of a thick material. So that is why these electron guns are having these electron guns. You can see from here, this is a 200 micron, and the tip will be somewhat here. That will be all the tips will be very small. These are all so this is a hairpin kind of structure. This is also a very thin, a very pointed structure, and in this pointed structure only the electrons will start coming out, right? So this is the reason, this is the fundamental mechanism behind the electron generation in an electron gun. And since tungsten having I think 3263 Kelvin, the melting point of tungsten is this much, so that is why we can easily heat tungsten beyond 2700 Kelvin, and we will get our electron. And electron and light both are coming out. It is up to us which one we want to use, how we want to use the electrons will be, let's say electrons will be coming out from this one, all the electrons. Then how we will use those electrons, since they are negatively charged, here I am writing electrons since are negatively charged. If I am to put some kind of positive potential, that potential may not be in the order of 10 volt or 100 volt, that potential may be in the order of some kilovolt, right? Let's say I'm putting some positive potential like 10 kilovolt, then the electrons will start coming in this direction. So that is how we are using the electron gun in a scanning electron microscopy to view our image, right? So this is the mechanism behind thermoionic gun, and we use tungsten and we use lanthanum hexaboride. The tungsten it gives us, so the one of the major performance of this electron gun is brightness. Okay, I think brightness I told in the first class, and the brightness is the the flux, the electron flux per unit solid angle. Solid angle represents the three-dimensional total angle, and the value of brightness, the unit of the brightness is area per meter square into stir radian. This SR is stir radian. Okay, this is the unit for solid angle, and this tungsten wire will be giving you brightness in the order of 10 to the power 8 ampere meters minus 2. Okay, but when we use the lab 6, what will happen? It will give 10 to the power 9. It is not much difference, but still we are getting more brightness. More brightness means more number of electrons are coming per second, are coming out from your material, right? And the more number of electrons are coming out, and also it will, this lab 6 is having a very large lifetime also, because we don't want to replace this tungsten or lab 6 on a daily basis, so that will cost us. So that is the reason we sometimes use tungsten or lab 6 if we want to get a better brightness. Then what is the mechanism behind the field emission gun? The field emission gun is, let's say I am having some kind of tip structure. Same thing that I am doing it here, the concept has been transferred to this field emission gun. How this concept has been transferred? I am having a tip here, the metallic tip. Generally this tip is made up of tungsten, right? I am applying some sort of voltage here. Which voltage I am applying? I am applying a very high voltage, let's say 20 kilovolt, or any random number I am applying. So this is a positive potential I am giving. Here also I am giving positive potential. So this is called as anode 1 and this is called as anode 2. Okay, I am applying too much positive potential, but when I am applying a very high positive electric field, then what will happen? The electron, without heating, the electron will start coming out. And what is the value of that electric field? That value of that electric field is 10 to the power 9 volt per meter. Okay, so when I am applying this amount of electric field, then only I will be able to generate the so when I am applying this amount of electric field, then only I will be able to generate electrons from my tip without heating, right? So that is what, that this effect is known as the electrons will start coming out. This effect is known as tunneling. Okay, and when so that is why you can see for a material, let's say I am applying some 10 volt. If I am applying 10 volt and but my electric field has to overcome 10 to the power 9 volt per meter, that means I have to make the tip, this meter is the tip radius 10 to the power minus 8 meter, then only I will be able to get 10 to the power 9 volt per meter, right? So 10 to the power minus 8 meter my tip has to be that small, so that I will be getting this electric field. Okay, and so that means 10 to the power minus 8 means my tip has to be in the order of nanometer, right? So which is extremely difficult. So that is why we do what, instead of reducing this tip, we increase this potential. We increase the potential and keep this tip radius in somewhat medium range, so that we will be getting 10 to the power 9 volt per meter. And so that is the reason the tunneling will happen, and due to the tunneling we will get all the beam of electrons. And there are three type of the field emission gun are there: cold, Schottky and thermal, right? And yeah, so this is one of the slides I am skipping. I'll come back to the previous slide next. So here you can see there are different types of so here is a tungsten, lab 6, Schottky and cold FEG is there. So how we are differentiating between this different kind of electron source, one of the main thing we are considering here, if you can see this column, this is brightness. If you can see, this is tungsten in the order of 10 to the power 10, lab 6 in the order of 10 to the power 11. That means only 10 to the power 1 increase. But here if you see 10 to the power 12 and 10 to the power 13 Schottky effigy and cold effigy field emission gun. So here from 10 to the power 10 to 10 to the power 13, if you see, the brightness will increase, and the brightness of the gun is one of the major performance parameter of our gun, because brightness we cannot increase later stage. Whatever brightness we are getting, we want as bright as our gun should be. Okay, this is one of the brightness is one of the major parameter. Another major parameter is this energy spread, right? Energy spread means, let's say I am hitting my material, or I am extracting the electron from my material by using electric field, but not necessarily all the electrons will be coming at only one coming out with only one energy, right? Some electron might be loosely bounded, some electron might be tightly bounded. So that means the energy variation will be there between between the electrons coming in the incident electron beam. So here if you see, in case of tungsten the energy variation is 3 electron volt, but in case of lab 6 the energy variation is 1.5. Here 0.7, 0.3. See, 0.3 electron volt, right? So that is the reason people prefer this cold field emission gun over this. So these are the thermionic, right, and these are the field emission gun. This is energy spread. And another thing, you have to look at lifetime. So these are all in this table contain all the information. So which are the major information I'm just telling? One is lifetime. If you see tungsten, in 100 hours you have to replace the tungsten. Why? Because electrons are coming means what? Effectively, the material over this area is coming out. So eventually, currently it is a sharp tip. Eventually after 100 hour of working, the tip will be like this. It will not remain sharp. Now what will be the problem? Once the tip will not remain sharp, you cannot extract electron. That you cannot extract electron as you are extracting in this condition. Let's say this is one condition, this is two condition. You will not be able to extract that much electron. And when that happens, the brightness will decrease. And brightness will decrease means the further down the column, all the problems you will also occur, and you will not get a good quality image, right? So 100 hour, here the lab 6 will be 1000 hour. However, you can see field emission gun 5000 hours you can use. So that is also another reason why we went to field emission gun. But there is a disadvantage associated with cold field emission gun also. Here you can operate in 10 to the power -2 to -4 this Pascal, but for field emission gun you have to go to ultra high vacuum. So here you can operate on high vacuum, but field emission gun you cannot operate in high vacuum. You have to go in ultra high vacuum. Okay, so these are the different kinds of electron source. And I want to come back to this another material, another component. Not this is not an electron source, but this is a component which is associated with the that electron source system, that is called as Wenelt cap. So why this Wenelt cap is there? Let's say my electrons are coming like this. It's a three-dimensional. You can imagine my electrons are coming in three-dimensional. I want my electron to be focused at a single point, right? What will happen? So this is my specimen which is far away. Currently not see. We should not say that this is close. Like this is not close. Okay. So this is far away. My specimen is there. So the moment this electrons are coming out, let's say I have put some positive potential, and I am starting to accelerate this electron, and electrons are coming in this direction at a very high speed. They will be coming in all directions, right? Since they will be coming in all directions, how I will first control them even before coming? Let's say this is my filament. If I am talking about, this is my filament and this is my anode. This is my first anode, and subsequently another anode will also be there. But here, just after coming out, they will be coming in all sorts of direction. If I do not give anything, then the number of electrons that are coming out and the number of electrons that my anode is able to accelerate, that will be a huge difference between them. So what what the microscopists do, they put a cap kind of thing. This cap is nothing but so this cap is called as Venel cap, and this cap is nothing but negatively charged, right? This is nothing, just a negatively charged component. So what does it do? Already electrons are so here if you see, already electrons are, they are coming out, and once they are coming out, here one strong accelerating strong anode is there to pull them in this direction. Only thing that I need to do now to change the direction, to give them directionality, right? So to go from all random direction, what this Venel cap does, this Venel cap gives them it actually it creates less divergence for the electron beam. This is the only reason that we put the Venel cap, so that this electron beam with less divergence go to this anode, and once they go to this anode will give them enough potential so that they will be accelerated. Then again the anode 2 will be there, it will also give the electron beam enough potential, they will again get accelerated. Our job is to make the electron beam as less divergent as possible. So to do that, Venel cap is a simple electrostatic lens which is negatively charged. This is one of the component in the electron beam system, electron gun system. Okay, and then comes the lens. Lenses will come. One will be condenser lens, another one will be objective lens, and also in subsequent classes you will see not only condenser and objective lens will be there, but also depending upon the microscopy method, you will see some projector lens in transmission electrons microscope, some intermediate lens also you will see in different electron microscopy. Okay, so lens aberration we have seen in our light optic system. Same things are also there in electron optics. Only thing is that here we have to take care of the lens aberration a little bit more carefully. Why? Because the electrons energy spread and the electrons deflection will be giving a much more distorted image as compared to the light optics. So here the spherical aberration means you will see that if the rays which is more from this lens this axis, optic axis, or the central axis if you want to say. Okay, so this is the central axis which is going through this black dot. The ray which is going away from the central axis, that will be focused somewhere strongly, and the ray which are coming close to the central axis, that will be focused here, right? And there will be in between, there will be the formation of disc that is called as the plane of least confusion. Okay, and the diameter will be given by this one. Okay, so this is what called as spherical aberration, and this spherical aberration so this is the spherical aberration, and so the coefficient, we measure the spherical aberration by coefficient of spherical aberration. Okay, so this is one of the aberration that we have to keep in mind while designing our lenses based. So how do we reduce this spherical aberration? By increasing or decreasing the magnetic field strength, so that our this incident beams do not go much more away from the optic axis, right? This is one aberration, and this is another aberration which is known as chromatic aberration. So chromatic aberration is chromatic aberration comes in light optics. Chromatic aberration was coming due to the wavelength difference, and subsequently from the wavelength difference the energy difference was coming. Here also same thing was there due to the energy difference, because the electrons will be coming at the energy spread, that means the delta E, right? Since the delta E will be there, the energy spread of energy of the one electron might differ from the energy of different electron. So due to that, different electrons will be focused at different point. This is the action of the lens, and there will be in between plane of least confusion. And this chromatic aberration is characterized by CC. It is known as coefficient of chromatic aberration. Okay, so this is one of the major. These two are two of the major aberration that we are we can see in an electromagnetic lens, right? And there are also this astigmatism is there, coma is there, and diffraction limitation is there. This to remove this astigmatism, one component is kept, that is called as stigmator. So there are lots of stigmator you will see in a microscopic column. If you see, okay, so lots of this is a microscopic column, and the stigmators are also there, so that the off axis electrons will not be deflected more. Off axis electrons means, I say, if you remember this, sagittal plane and tangential plane, which are focused by electromagnetic by optics, the glass lenses at different points. So that's what here also those kind of different those kind of refraction is there, and due to which astigmatism come and coma. And another thing is also diffraction limitations. Okay, and one thing I want to say, diffraction limitation means if we want to measure this diffraction limitations, 0. Sigma divided by alpha. So how come this alpha come? We know that the resolution, okay, the D optimum 0.61 lambda divided by sin alpha. And we know that from electron we do not want to the angle that the most oblique electron which will be deflected is not that much great, that is not high, so it is very, very low. So for small angles we know that sin alpha will be alpha. So if I want to put that thing that here, so that means I want to reduce the reduce the electron beam, which are reduce the electron beam to be less diffracted. Then in that case, if you see, this alpha is the semi apex angle. Okay, and here another thing I just want to see here. If you see this formula, let's say in this case, either this case or this case. So here if you see the diameter of the spherical aberration, that is directly proportional to, so here they have taken the beta term. So this beta is the semi apex angle, they have taken it here. I am denoting it as alpha, so it is directly proportional to beta q here, right? So this is the spherical aberration, right? So in spherical aberration, here if you see, if you want to limit the diffraction, the alpha should be, if you are increasing alpha or the semi apex angle, this will be decreased. That means the diffraction, the aberration due to the diffraction of the electron while they are traveling through the lenses, it will be limited. But if you increase this alpha, or whether alpha or beta, I am talking a semi apex angle here. Okay, but here so okay, I will write it as alpha, not beta. Yeah, so you can, so now increasing semi apex angle, you are reducing this diffraction limitation. But now increasing this semi apex angle, you are increasing the effect. ds means the diameter of this diameter of the least plane of least confusion. Due to spherical aberration, we are increasing the spherical aberration. So it is in microscopy, in electron microscopy, you have to choose a optimum value of alpha, so that you will get a perfect good image. It is not a thumbs rule or a hard and fast rule that you have to be within a certain angle of you have to choose a certain angle of semi apex angle because one thing will increase one semi-apex angle might increase your spherical aberration, while the same thing will decrease some other aberration. So always you have to keep an optimum between all these values. Okay, and now after coming coming all the way through the electron column, in the scanning electron microscope, the electron hits the sample. Okay, and always remember, once electron hits the sample, all kind of rays will be generated here. It is not that we will only get secondary electron, it is not that we will only get X-ray or anything. Always I am considering this thing as a concept of thin electron, the thin specimen, sorry. Why thin specimen? Because otherwise the beam cannot penetrate. Since the beam is penetrating here, I am considering a thin specimen. I want to see what different kinds of rays are generated when my incident electron beam is interacting with my material. So backscattered electron will be generated, secondary characteristics X-ray, visible light, and some electron will also be absorbed, and due to this absorbed electron, sample might be heated also, right? And then Bremsstrahlung X-ray, inelastically scattered, elastically scattered X-ray. All sorts of beams are generated when your incident beam interacts with your specimen. What kind of image or what kind of information we want to see, based on that we will put our detector, and the position of detector, and based on which information we want, the electron microscopy gives us those features. These are all forward scattering rays. Okay, and these forward scattering rays generally we collected using transmission electron microscopy, and these all are backward scattering rays, and these backward scattering rays we collect in ACM. Not all of them, but we generally collect back scattered electron, we collect secondary electrons, and we collect characteristics X-ray. Right? These three we collect in our scanning electron microscopy. Okay, and there are two kinds of scattering happens. One, this is the incident electron beam. Okay, this is the incident electron beam which is coming and hitting the sample, and when the incident high energetic electron beam comes and hit the sample, then what will happen? Elastic scattering happen. Elastic scattering means my incident electron beam will not lose energy. It might get deflected. Okay, it is not that it will not deflected, it might get deflected, this beam, but it will not lose energy. Inelastic scattering means it will lose its energy, not completely, but it might also completely lose its energy, but in a broad range of energy spectrum, this incident electron beam, if it loses energy, that is what known as inelastic scattering. And remember, so when my incident electron beam is interacting with my sample, so it is not necessary that it is interacting with all part of the sample, right? All the part of my sample, it is not necessary. So the part of the sample which my electron beam interacting, this, it's like this structure, this is what called as interaction volume. Okay, so the interaction volume is the three-dimensional space beneath the sample surface over which the incident beam spreads due to elastic collisions. Okay, and in this interaction volume sorry, so depends so whatever the rays we saw here in this backward scattering, the backward scattering rays, all the rays will be coming from this interaction volume, right? Back scattered electron will come, secondary electron will come, Auger electron will come, X-ray, light, all those things will come. And how they will come? They will come depending on the depth, penetration depth of the incident beam, like how much in depth the electron beam has interacted with the material. Based on the depth, the incident electron beam interacts with the material, and from that interaction volume, different kinds of rays are coming, and which detector, based on which detector we want to put the we get the microstructural features, right? Like you can see here till 5. So there are 5 nanometer here, 150 nanometer here, 1000 nanometer here, right? So so based on different penetration depth, different kinds of electrons are coming. Okay, like generally secondary electrons are they come from 3 to 50 nanometer. Below that backscatter, so this is secondary electron. Below that backscattered electron comes, because backscattered electrons are having a much larger energy, right? So yeah, now we'll see the secondary electrons. Secondary electrons are the electrons whose energy energy is less than 50 electron volt. Remember, here we are talking about high kilovolt of energy, right? But here electrons will be emitted, the energy of the emitted electrons is less than 50 electron volts, and generally it comes from few nanometer of the surface. And they are categorized as secondary electron 1, 2, 3, 4. So 1, 2, 3, 4 means, let's say incident electron beam is coming, this is my sample surface, and the point of entry, just when my incident electron beam interacts with my sample, a few electrons will be going out, and those are known as scanning electron 1. Sorry, not scanning, secondary electron 1. Then this is my incident beam, then incident beam will go interact with the material, and then at the point of exit, when it starts to go out of the material, it will also give some of the energy to a few of electrons in the material, and those electrons so this is point of entry. So those electrons at the point of exit are known as secondary electron 2. And then secondary electron 3 and secondary electron 4 are not associated with the sample, rather they are associated with the secondary electron 4 is associated with the beam, incident beam. During incident beam coming, let's say aperture is there, we are putting one aperture, and here let's say some secondary electron escapes, so those are secondary electron 4. And once the incident beam interacts with and then goes out, and then aperture stops it, from the aperture some sort of secondary electron comes out, they are known as secondary electron 3. So based on this, secondary electron are categorized, and generally secondary electrons are the loosely bound electrons to the sample. Okay, and if you increase the tilt of the sample, let's say currently it is like this. Okay, if you increase the tilt, means this from this angle. Okay, more and more electrons will be coming out. Why it will be happening? Because it will come and easily it will at a less penetration depth it will interact, and then at the point of exit secondary electron 2 are going at a large number. We always prefer there should be much more secondary electron 2 secondary electrons should be there. Okay, so by tilting the either sample or tilting the beam, any one of them is favorable, and these they come out generally due to the edge effect. Edge means if we have a flat specimen, right? If we have a flat specimen and then we have a tilt kind of specimen, then what will happen? Let's say my electrons are coming and it interacts. Okay, here it interacts, one beam which is interacting with this, and here also another beam will. So the point of exit for this incident beam at a edge structure, it is much more easier. Okay, because it came and the path is very slow for the path is very less for its exit, so that is why it is quickly able to exit, and during exit it is generating all those secondary electron 2. While if it is coming at a normal if it is falling on a flat surface, then it will go and again it has to go back, then while going from the sample it will generate secondary electron. So this is a little bit tedious, and this one also takes time. This is quickly happens because of the edges, right? Let's say one electron comes here and immediately the incident beam goes out at the edge and it will generate some. This is the incident beam, this is secondary electron, right? And then comes backscattered electron. Backscattered electrons are electrons which are having energy greater than 50 electron volt. High atomic number, high will be the backscattered electron. Yeah, the graph between the electron yield and the atomic number, you can see as you go in the increasing order of atomic number, the backscattered electron will also increase, right? And so these are the electrons, backscattered electrons are the which electron? The incident electron that reverse direction with minimal energy loss. Okay, why they reverse their direction? Because in the sample there will be nucleus, okay, which will be positively charged. Many more nucleus will be there in the sample. Let's say I'm talking this as a sample, many more positively charged nucleus will be there. So when my negatively charged electron beam will be there, so it will attract. Okay, all the positive charge will be attracting to the to this incident electron beam. So that is why it will not be able to maintain that straight path, because the accelerating potential is between 5 to 30 kV, right? So it will start deviating due to the affection created by this positively charged nucleus. So that is why it will start deflecting. And the more since this nucleus will not be having that much energy to absorb all this electron, to absorb the energy of this incident electron beam, so that is why it goes with minimal energy loss. Okay, little bit of energy it loses due to this positive since it changes its direction, and while going also it gives some of the energy to the electrons around this nucleus, but with minimal energy loss, these backscattered electrons we are getting. Okay, and they have huge escape depth. Huge escape depth means when I was talking about secondary electron, I was talking like 5 to 50 nanometer for secondary electron, but they can the backscattered electron, they have a very high penetration depth than secondary electron. Okay, so that means the backscattered electron can go deeper into the material still, because backscattered electron is the incident electron and they are having very high energy. So that is why they are able to go deep into the material, interact with the material's grains or any kind of features, and then they can come out, right? So they have huge escape depth, and this is the, you can see electron yield. As you increase the atomic number, the secondary electrons will not be the yield of the secondary electrons is not increasing that much. But if you can look at the backscattered electron, as you increase the backscattered number of backscattered electron will be high. So this is the reason why we want to use backscattered electron for our phase contrast in a scanning electron microscope. Because let's say I am talking about two material, aluminum and zinc. There are two materials are there in my material system, aluminum and zinc. And if I want to see which one is aluminum area and which one is zinc area, what I will do, I will use this backscattered electron. And since backscattered electrons coming out of this zinc, who will be interacting with zinc, they will be much more as compared to this backscattered electron which will be coming out after interaction with aluminum. So this zinc will be looking brighter and aluminum will be looking a little darker. So I will be clearly able to see which one is which. Okay, and there are a few parameters also, like probe size, resolution and brightness. Probe size is the size which the condenser when the condenser converges the electron beam. And then resolution, we know what is the resolution. The resolution same like it is the minimum distinguishable distance, and the brightness is density per unit solid angle. And this brightness is given by, I am talking about current I. So this intensity is current per flux, right? Current per flux means so the current per area, that means the flux. So I am talking about area, let's say d by 2 square, and the unit solid angle is given by if I am talking about the solid angle is alpha. Let's say I am talking about the solid angle. So the solid angle, if it is alpha, then the unit solid angle will be given as pi alpha square. So that is pi alpha square. So this gives us 4I pi d square alpha square this square. So now you see based on the probes, so there are three different parameters are there. One is brightness, another one is, this is 4, another one is resolution. So brightness is defined by beta, resolution is given by d. Okay, resolution is given by d, and then another thing is probe size. Probe size is given by I. Okay, so If you want to get good probe size, then you have to increase the I, but that will decrease that will also, so yeah, here I. So if you are going for higher D, okay, if you are going for higher D, that means your brightness will decrease. If your brightness will decrease, then the probe size here, the current will also start to decrease. So based on this parameter, the beta, the I and D, you have to find an optimum value between these three parameters. Okay, and in ACM lens, remember, in light optics lens we are talking about magnification. In ACM we are talking about demagnification. Why demagnification? Because we are not seeing the entire material at a particular point. We always see this material in a our object is, let's say, like this, but the electron beam which is falling on our material, it is very small, it is a very fine point, and it scans like this. It is not a continuous, it is a continuous scan, but it first, let's say this is A, this is B, then another point, this is A dash, this is B dash. So first it scan in this direction, A to B, then again it comes back and it starts scanning again in this direction. It does not come from B to A. The scan does not happen from B to A dash, right? That is why it is known as a raster scan, and it scans each the electron probe size is very small. Okay, probe size means the final diameter or the final size of the electron beam which falls on the sample. So there are three kind of currents are there. One is emission current, which is coming from the electron gun. Another one is the beam current. The beam current is the current which after convergence by the condenser lens, which the current which comes, that is called the beam current. And finally the probe current. Probe current is the current which fall the electron beam which falls on this specimen. Okay, so there are three different kinds of electron beam are there, and in ACM lens the demagnification is always greater than 1. Why? Because the demagnification is given by P by Q. P is the object size and here the image size. The magnification was image size by object size, and here the object size by image size. Okay, it is the reverse. Okay, and for ACM lens, the demagnification of the source size and the semi aperture angle, if I am talking about alpha, they happen by the same factor. Okay, so these are the important image formation parameters with which we generally create an optimum value, so that we will get nice and good microstructural features. Okay, and these are the different imaging modes and operation. So one of the imaging modes is we working. So what will happen if we increase or decrease the working distance, and same thing what will happen if we limit our aperture size, as well as there is another parameter is also there, that is convergence angle. What will happen when we increase or decrease our convergence angle? Okay, based on those parameters we put our sample and we want to image our material, right? So I think that completes our discussion for today, and we'll be going through, so based on these topics we'll be going through a few conceptual questions. Okay, so these are the questions related to the operation of ACM. So far we have not in ACM, since the concepts of ACM are not completed, because in the next week also we'll see some more different modes of the ACM. So it is not completed, so we'll not have any numerical questions this week. We'll be going through the concept which we have, the theoretical concept which we have covered it just now. So the first question I'll be seeing. So what type of signal will be used to get the maximum contrast as shown in the figure? Okay, so the first option is secondary electron, the second option is backscattered electron, and the third one is X-ray diffraction, the fourth one is phonon scattering. So whatever we have discussed today, can you answer the question, any one of you?
Sir, B, sir.
Yes.
Backscattered.
Yes. So maximum contrast is generated in the backscattered electron. This is the correct answer because the contrast, those kind of contrast come from atomic mass difference, and this contrast is much more higher than the secondary electron, the contrast generated by secondary electron. In fact, if we want to see, let's say I prepare any material, if we want to see, we will see in the subsequent questions, if we want to see any kind of phase, secondary phase or any other phases are present or different kind of precipitates are there, anything we want to see apart from our parent material, we go to this backscattered BSE mode. That in the imaging mode we say that it is a BSE mode, and this there for BSE mode there are different kinds of detectors are also there. I think we will go through those detectors in the next week. So those detectors will detect. So the yeah, so the correct answer is backscattered electron. So yeah, so next question is: a polymeric and powder sample properly coated operating at 20 kilovolt is excessively charging during secondary electron focusing. How the operator can take proper imaging? So I have told that so regarding this there is a concept. So electrons are highly charged particle, right? So when they come, there is a provision that let's say this is my sample and electron is coming, and this ACM, this scanning electron microscope, and this stage is made in such a way that, let's say this is my sample, and it is made in such a way that these things are grounded, so that these are negatively charged. Let's say they start accumulating on top of my sample. If they start accumulating on top of my sample, then after some time these all incident electron beam will be covering my sample to area totally. So to remove, to avoid that kind of imaging, to avoid that kind of limitation in ACM, these things was the ACM is grounded, so that whatever the electrons are coming, they easily will be transferred through this direction to the ground. But this thing happens, electron can transfer easily to the ground in case of metal or in case of any conductor. But in case of insulator, let's say a polymeric sample or a powder sample, let's say a ceramic sample which is not conducting, some ceramics are conducting, a ceramic sample which is not conducting, right? In those cases what will happen? In those cases the electron will come, and since they will not, they cannot conduct, the rate at which the electrons are accumulating on the surface of the material is far greater than the rate at which the electrons are going away going through the material and getting grounded here. Okay, that means the electrons will be they will be accumulated over here, and then there will be, after some time what will happen, since these electrons are accumulated on the surface, they will also start to repel this incident electron beam. So to avoid this kind of structure, you will not, in this case what will happen, you will not get a good image. So to avoid this kind of thing, what we do generally, we coat this material on this non-conducting material, we coat with a very thin layer. That thin thickness is 1 to, you can expect 1 to 10 nanometer layer of gold coating with the material, and that gold coating is connected, that this is, let's say this is the gold coating, and this gold coating is actually connected with a carbon tape, and that carbon tape is connected to a ground and that thing. Then finally this is the way that we discharge all the electron of the incident beam from our sample. Okay, so this is one reason that we put some gold coating over here, but still after putting gold coating, so this and this question comes, it's a non-conducting sample, we have coated on top of it, and then we have put the carbon tape, we have given sufficient region so that the electron will not start accumulating on top of our sample. But still this condition comes, then what will be the answer? The operator should reduce the EHT. EHT refers to electron high tension. Okay, The operator should reduce the EHT value, the operator should change the operating mode, the sample can be imaged. Which one will be the correct answer? Can any one of you guess? Okay, the correct answer will be A. The operator should reduce the EHT value. What do you mean by EHT value? The accelerating voltage, this is the electron high tension or the accelerating voltage. So the accelerating voltage means the more amount of electrons are fluxed out of the electron gun per minute or per second, right? So if we want to reduce the amount of electrons, if we want to reduce the amount of electrons which are falling onto our sample, then we can reduce this EHT value. So the moment we reduce this EHT value, the less number of electrons will be falling onto our sample, and then the charging, if the charging is happening, then it will reduce the charging. It will not completely eliminate the charging, because since we have quoted there will be some amount of charging, but still it will reduce the charging for the time, so that we can take an image. Otherwise what will happen, you cannot take an image. If charging happens, then immediately your image will start wobbling, and it will many distortion you can see in your image, right? So for that time being, for that second or for that microsecond, you just want to reduce your electron high tension, so that you will take the image of your sample. Okay, so and you cannot change the operating mode. Why the operating mode? Because this is taken in AC, let's say secondary electron mode. So you cannot go to BSE suddenly, because BSE generally operates at a little bit higher operating mode. So you cannot see the BSE. If there is no phase contrast difference is there, then there is no point to going in BSE. And if the sample can't be imaged, so that should be the last option if you are having some biological sample or anything. But if you have to image the sample, then you have to tell the operator that he or she should reduce the EHT value. Okay. Then comes the third question. A fractured sample micrograph is shown in the image. What kind of signal was used for analyzing the specimen? So this is a fractography image. Okay, so fractography image means different kinds of structure you have to see. That means different kinds, like this is looking like a hill structure, this is looking like a valley structure. So what kind of mode, operation mode, or the electron that you want to use for viewing this specimen? So first is secondary electron, another one is backscattered electron, third one is ion beams, fourth one is visible light. Can you answer which one is the answer?
Sir, yes, sir, secondary electron.
So secondary electrons are the correct answer, and the secondary electron generally comes from 3 to 50 nanometer layer. Means the top of the layer, they come from the top of the surface they come, and due to the amount of variation that we will get from due to height difference, that we get a little bit of contrast. As you can see here, this region is a brighter region. It does not mean it is having a phase contrast, right? It is in secondary electron, the contrast that you get, it is because of the height difference. Since this is at a much higher height as compared to this one, so it is giving much more brightness than this one. So we use secondary electron to see fracture, to do fracture analysis or the fractography study. So definitely we cannot use the ion beams, because ion beams are extremely powerful, much more energetic than electron beam. You want your sample, even let's say ceramic sample or a composite cermet sample, you want your electron beam to fall on your sample, but you do not want the ion beam to fall on your sample. There is a process you will see, you will know, that is called as focused ion beam, FIB, which is used to prepare the specimen in TEM specimen preparation. There they use gallium beam, gallium ion. Okay, so here gallium beam is there, and it is a ion beam. So here we cannot here ion will also give you an image, but you cannot keep your sample under ion for far too long. Otherwise what will happen, it will immediately damage your sample after some time. So to view this focused ion beam is generally equipped with ACM. What is the job of ACM? Through electrons, you want to view the area that you want to measure something, you want to take out some sample for the TM. So you view the area through electron, you cut the area through ions. Okay, so this is one technique, just remember, I want you to remember, that is called as focused ion beam. Okay, so ion beams are definitely not advised or preferable for viewing the sample, and visible light, because of its wavelength is too much high, it cannot detect the topographical features. Here this is the figure shows contrast in gallium nitride chip in a mixture of light emitting diode. That means this is the my parent material by a mixture of light emitting diode, E scrap. That means this is my parent material and this is my secondary material, right? So what type of signal was used for this? A is a secondary, B is backscatter, C is X-ray, D is phonon. Can any one of you answer?
Backscatter.
Yes. So it's an easy one. So we want to any phase contrast if we want to see in scanning electron microscopy mode. So that is BSc detector will give you. And this phonon, what is phonon? Phonon is a lattice vibration. X-ray diffraction signal. X-ray will not map your material. Remember, X-ray will always give you it gives the phase identification in terms of intensity. X-ray. Okay? It is X-ray gives you the phase identification of your material in terms of intensity and position of the intensity, and the secondary electron will always give you topographical information. So the correct answer would be backscattered electron. Okay, yeah. So which of the following is true for the following interaction volume? So there are two scenarios. One is A here, another one is B. So A says that A corresponds to high accelerating voltage, B corresponds to high accelerating voltage. We have talked about interaction volume. Interaction volume is the volume that means the three-dimensional space beneath the sample surface with which the incident electron beam interacts. So can you guess which one is will be the correct answer? Question number 5.
D.
That means B corresponds to high accelerating. Yes, that is the correct answer. B corresponds to high accelerating voltage means the higher your accelerating voltage, let's say I am saying taking it as B, so it will have much more higher energy for the same material. If I am talking about the material, it's same, so it will have higher energy. If it is coming with higher energy, then there is a chance that the interaction volume will be much more higher as compared to this case. This is A case, this is B case, so interaction volume of B will be higher than interaction volume of A. And what happens when interaction volume increases? We will get much more information in case of B, right? We will be getting information from large area of the sample B than we are getting from the sample A. So in that case, you can say that we can increase the accelerating voltage even more, but when you increase the accelerating voltage, in that case the aberration, the lens aberration and the electron column also, they will also start acting. Okay, so that is why we always have to maintain a minimum, maintain optimum value, and there is also a high chance that if you increase the accelerating voltage much more, then you can damage your sample. Okay, since we are we are seeing the images of our material in a reflectance mode, we are scanning the material, so that is why the B, so we want an optimum balance of accelerating voltage and our resolution and aberrations also. Okay, so B corresponds to high accelerating voltage. Yeah, so the question number 6 is, on what factors do the intensity of secondary electron depend upon? So first is shape of the irradiated object. So irradiated object, this is my material. Okay, irradiated object. Intensity of secondary electron. So remember, secondary electron always come from my material. Mostly secondary electron 4 is a different case, but we will not always consider that thing. But secondary electron If I am talking about secondary electron, then we are considering that it is coming out of my material. Okay, so shape of the irradiated object, option A. Chemical composition of the irradiated object, option B. Number of electrons ejected. And then option D is size and chemical composition of the irradiated object, number of electrons ejected and number of electrons reabsorbed by the surroundings. So can you guess which one is the correct answer?
B.
B for Bombay, right?
Yes.
Sir, A, sir. A, shape of the irradiated
Okay.
object. A.
Okay. So one option is A, another option is B, right? Okay, so these though individually they are the correct answer, sorry, not shape of the irradiated object is not the correct answer. B, though it is it is also a part of the correct answer, the correct answer is D. Why the correct answer is D? Because shape of the irradiated object does not matter, because the interaction volume matters, right? Which shape, whether my material is triangular in shape, whether my material is rectangular in shape or circular or some star kind of structure, it does not matter that what is the shape of my material, but what kind of material I am having, that matters. So B can be an answer. Number of electrons ejected, if I interact, my beam is coming and interacting and giving a interaction volume here, right? So number of electrons, how many number of electrons it ejected from this sample, that also will give me some information about the surface. So this might be also answer. That means size and chemical composition of the irradiated object. So if the size of the irradiated object is thin, then that will also give me some different contrast. If my size of the object is thick, that will also give me a different contrast, because based on the size also my interaction volume will change, and since my interaction volume will change, then the information that I will get from the surface and beneath the surface features, that will also change. So size and chemical composition definitely, because if I am having different material, different element or different phase in different structures, then that will give me a different contrast, because phase contrast is definitely I can get from BSE mode. And number of electrons ejected, how many scanning electron microscope like number of electrons ejected means, let's say and there is a topographical contrast is there, right? Based on the size, how many electrons, whether my surface is flat, whether my surface is a hilly kind of structure, that information I will get based on the number of electrons. And number of electron reabsorbed, it is not necessary that all the electrons which are coming out of this my material, they all will be going to the detector. Let's say I am putting my detector here, they might be reabsorbed, because they might get deflected with some other electron, and then they might not at all reach this detector. So that is also another factor. So size and chemical composition, definitely. Number of electron ejected, it is also a possibility, because if I do not eject, if my incident beam is not able to eject number of electron, then I will not get that complete information. Okay, and this is electrons absorbed by the surroundings, right? So this all all of the options are correct. So that means D will be the correct answer, size and chemical composition of the irradiation object. So here I have written BSE. BSE will only give you phase contrast, right? Here also chemical composition you will get. How you will chemical composition you will get, if you want, and if you do an EDS, energy dispersive spectroscopy, you can do energy dispersive spectroscopy in both mode, AC mode as well as BSE mode. So that will also give you the secondary electron is written here. So if you will do an EDS, energy dispersive spectroscopy, you will get the chemical composition of the irradiated object. Okay, so D will be the correct answer. Yeah, so the next question is, secondary electrons are useful for microstructural study in SEM, while BS electrons are useful only for diffraction study such as EBST study. Is it true or false? Can anyone answer?
False.
Okay. Yes.
False.
Yes, this is the correct answer. So secondary electrons are used for microstructure study, BSc are not. So EBSD means electron bags scattered diffraction. You remember diffraction, I told in the first class that there are different pattern point will be there in the diffraction. So this is a single crystal diffraction, then there will be structure, ring kind of structure. Okay, so these are the diffraction pattern if we are talking about. So it, and there is also, so these diffraction pattern we get in TM. If you want to talk in ACM, there is a pattern called Kikuchi pattern. In the next class I think you will study the Kikuchi pattern. So Kikuchi lines will be there, these kind of different set of paired lines will be there. You will see different paired lines will be there, and the distance between different paired lines and how they are oriented will give us orientation information. Okay, so that is that Kikuchi pattern. So this is called as Kikuchi diffraction. So this information we can get it from ACM as well as TM, but ACM the EBST study heavily dependent on whether you are able to get a nice Kikuchi pattern from your material initially, then only it will go to crystal orientation, and you can use the orientation image mapping process to see the orientation of your grains in the material. So though the diffraction, we employ the BSc electron for on not only so BSc electrons are useful for diffraction studies such as EBST. No, BSc also that will give you phase contrast. One of the main job of this BSc mode is to give phase contrast. Any difference in the phase or even any difference in the elemental analysis, the difference different elements are there, BSc backscattered electrons will be giving you. Okay, so yeah, secondary electron generated from more than 2 nanometer depth cannot emerge out of the specimen, whether it's true or false. Can anyone answer?
False.
Yes, that's a false thing, because secondary electron is having penetration depth of 3 to 50 nanometer. They can emerge out they can emerge the pair once from the penetration depth of 3 to 50 nanometers. Okay, so that is the correct answer. Yes, depth of field of scanning electron microscope will increase when, so depth of field means it is associated with the specimen material. Depth of focus is associated with the image, right? So the depth of field of scanning electron microscope will increase when objective aperture diameter will increase, magnification increase, working distance increase, none of the above. So here I'll tell you, so the objective aperture diameter will increase. What happens when the objective aperture diameter is increasing? That means we are allowing more and more amount of incident electron beam to fall on our sample. Let's say this is my sample, we are allowing more. If we are going in this direction, my aperture, this is the objective aperture. Okay, if it is increasing, if it is opening, then we are allowing more and more number of electrons, but it has nothing to do with the sample, because sample will be staying here. Let's say electrons are coming also in some oblique direction, right? They all will be falling on my samples. Okay, then magnification increases. Electron will increase when magnification increases, not necessarily, right? Because magnification can increase. It is not necessary that when we increase the magnification, depth of field will increase, right? So this is also not correct. This is also not correct. Working, none of the above. Okay, we'll see. Working distance increase. Working distance increase means, let's say this is my focal point. From here, earlier this was my focal point. Now my focal point is somewhat here, right? So working distance increase means, so this was the final aperture to earlier working distance W. Now my working distance is increasing here. So working distance is the distance from the final aperture to specimen. In this case, objective aperture to specimen. Let's say I am talking it, this one is objective aperture. So this is W dash. So this has increased means my depth of field of scanning electron microscopy will increase. If my working distance increases, then what will happen? They might, so initially they were all focused, all the incident electron beams are focused at this point. Now what will happen, if I increase my working distance, they will be focused at this point and then they will be going and falling on the sample. So that means I can see different features of my samples, right? So the depth of field means I will be, my image or my object will be in focus, right? So at that time, if I increase my working distance, my many part of my object will be in focus. So this will be a correct option, and since many part of my object will be in focus, so the depth of field of also scanning electron microscope will also increase. Okay, so at the same magnification I'll be able to see various features, and that various features includes the like flat surface as well as hilly kind of area. Yeah, so this is about the current that I was talking. We'll go through this
Around a
quickly.
small question in the previous one, whether that will affect the resolution,
Whether
whether increasing the working
yes,
distance will
yes,
affect the
yes, yes,
resolution.
that will affect, yes. So that is yeah, that is why it is not always also advisable to change the working distance, all means always to change the working distance, because there is a generally in scanning electron microscopy we keep a fixed working distance, and if we want to see other thing, like we want to see other features, then we change the like beam current and all other things we change. We generally do not change the working distance, so it will affect resolution. That is correct, because the probe, in that case what will happen, the probe diameter will also increase, and once the probe diameter increases from a nanometer to, let's say, 1 digit nanometer to 2 digit nanometer, it will affect resolution. Okay, and yeah, so this is about the current. The portion of the electron current that leaves the gun through the hole in the anode is called as, can anyone answer? This is I have told about the 3 current, but this is a little bit tricky. So the portion of the electron current that leaves the gun, so till this much leaves the electron gun till this much, it is known as emitted current. Okay, through the hole in the anode, in the anode means this is my electron gun, it has come out, but in all sorts of direction, this is called emitted current. But since my anode is there, it is converging, it will be the, this is called as first crossover. Okay, it is not necessary that some electrons will be going in some direction, they might not form this first crossover. So all the electrons which are coming and meeting at the first crossover, beyond that all these electrons are called as beam current, because this is our electron beam, and this electron beam we want to put it on top of the sample. Okay, so this is what called as beam current. And finally, out of them also, when we put our objective aperture, right, we do not want all the electrons to go and fall on our aperture, then finally when it falls on our sample, that is called as probe current. So this the answer to this is, the portion of the electron current that leaves the gun through the hole in the anode is called as beam current. Okay, and yeah, in an electromagnetic lens, the magnetic field exerts force on a electron moving in a direction perpendicular to the direction of field, perpendicular to the direction of propagation electron, parallel to the direction of propagation of electron, perpendicular to both direction of electron field and direction propagation of electron. Can anyone answer?
Sir, B is the answer.
Yes, that's the correct answer, because initially what will happen, the force will be only at the a point of entry when the electron beam gets to feel the force of the magnetic field. At the point of entry, only the perpendicularly the force will be there, but the resultant of that perpendicular force, it will change its direction. The moment it changes its direction from perfectly perpendicular to some little bit here and there angle, then all the perpendicular and as well as the direction of propagation of electron, that will also feel the force now. So that's why the spiral and helical path will be there. So D will be the correct answer. I think this is the last question. We'll go. So crystal structure and grain orientation of the specimen are obtained from which signal? Can anyone tell?
Sir, B, sir, BSc.
Crystal structure and grain orientation of the specimen are obtained from BSc signal. Grain orientation. Okay. Any more answer?
E.
Sorry.
E, sir.
Okay. AC signal. Okay.
C, X-rays.
C. Crystal structure and grain orientation.
It will be A, I think.
It will be, yes.
A.
Yeah, so the answer will be A. Crystal structure and grain orientation. You will get it from the SE. The BSE will not. So this is X-ray will not give you the grain orientation. Okay, X-ray will. So this is the I versus 2 theta. X-ray will not give. Bremsstrahlung X-ray is the white X-ray. Okay, white radiation. It will not give. So this is the characteristic X-ray I am talking about. So it will only give you the position. BSE, it will not give you the grain orientation. Okay, in which direction the grains are there. It will give you the phase contrast. The secondary electron will give you the crystal structure and the grain orientation, because in secondary electron you can clearly see, right, clearly see in which direction your grains are there. Okay, so grain, though in EBSD, if you if you want to see the what is the orientation relation between the between different grains, then you have to go to electron backscattered. In that way BSE will be useful. The relationship, if you want to see that one grain another grain, what is the relationship between them, you can go to EBSD. In that way BSE will be helpful. Otherwise, if you want to just see the microstructure, the crystal structure, what is there, then it is the secondary electron will be giving you the. Okay.
I have a query.
Yes, please go.
Sorry, I just something I could not follow because I was traveling. Anyway, this when we do the EDAX analysis,
Yes.
always we do BSc.
Okay.
Generally, that I have seen the people are doing over there.
No. The
And
EDS analysis you can do both in SE mode as well as BSE mode.
okay, you are trying to say that both mode I can do that.
Yes, in both mode you can do.
But I have seen 2-3 places.
Mhm.
Generally, they prefer the BSc mode. Any reason behind that?
BSE
Preference
mode,
I'm looking.
no, BSE mode, they want to go for BSE mode because they might have different phases. If you are not having different phases, then you can take the BSE mode, because they will be, then in that case they will be easily identify which element, let's say we want to do a spot analysis, they can easily pinpoint that this at a particular, let's say I am talking about this thing, this is a material and top of which this is a precipitation is there. In BSE mode if you go, then only you will be able to see this that this is some other material, this is some other material, right? So that is the reason people go for BSE mode. Otherwise if you are not suspecting any phase segregation or nothing, then you can go for SE mode as well.
Okay. But why this difference we can see? That's the same thing I can see in AC mode also.
No, AC mode you can see, if AC mode if you can see the contrast, it might it is AC mode will not give you phase contrast. AC mode will give you the topological contrast. That means the surface or any kind of due to height difference, the topological contrast you will get. You will not be able to say that my phase has segregated or I am getting a different phase.
Reason, can you please repeat the reason?
SE and BSE?
No, BSc, that why this difference we can get it.
Backscattered, because it is you if you see the backscattered yield, if I am talking about, and this is the atomic number, the backscattered yield is like this. So the more you go for this higher atomic number element, the more backscattered electron you will get from your specimen, and that is the reason you will see the contrast will be higher. So this is the backscattered electron yield, if I am talking about. So the curve goes like this. It is a very huge number. I will show, I think I have shown it here. Yeah, here if you see the yield will be very much for this. As you increase the atomic number, the yield will, the number of backscattered electron will be increasing, while the number of secondary electron, they are not increasing they are not increasing that much. They will be increasing, but there will be very, it is not perfectly parallel. This line is not perfectly parallel to this line, but in the case of backscattered, you can clearly see the oil. That means more number of backscattered electrons will come out.
I have one more query.
Yes, please.
You see, we see a lot of reports where we see the SCM images and we see the EDAX analysis also.
Okay.
And EDAX analysis, we can see the count and that intensity, the scar.
Yes.
Now, generally, I want to understand that how much count should be their standard process, some guidelines. How many this? See, if I give metallurgy is a beautiful subject, over a period of time we'll experience. If you give 4 labs, 4 different ways, same thing they will do.
Okay.
Correct?
Yes.
Like someone who is for example, 1,000 count, someone do the 5,000 count, someone do
Depends.
the.
Yeah, I get it. It depends on the actually detector. It has nothing to do with your material. It has more to do with the detector, I would say, because the more some detector are equipped to give you high counts, and some the detectors are equipped to give you low counts, but their signal to noise ratio will be very high. So in that sense, same material, it's like say, if you do a simple X-ray analysis, same material you take to 2-3 different X-ray detector, they will give you different intensity count, right? So that will that sense you can understand the electron. So there also we are counting the photon, here also we are counting the electron. So it's based on the detector, that how much the detector is able to capture the emerging electrons.
I request if you can some comparison study you can give it will be helpful.
Regarding the count, okay.
Regarding the count, because many of
I
the
will
cases
tell you the count.
we
I will tell you how the counts are actually. We'll get. Means in the next class, I will bring that photo. We'll see how the intensity, how it is varying. Because intensity is nothing but count per second. That is what the intensity is. So based on the detector, you will get the count. I will try to get that image when I will try to get the image, and I will try to explain it to you.
please, thank you.
Yeah.
Sir, I have one basic doubt.
Yeah. Please go ahead.